Think of a function as a machine. You feed a number in, the machine applies one fixed rule, and a single number drops out the other end. Feed in 3, double it, get 6. Same input, same output every single time. That reliability is the whole point. But there is one unbreakable rule. Each input may give only one output. If a single value could come out as two different answers, the machine is broken, and we no longer call it a function. One in, exactly one out. Hold on to that, and the rest follows. A mapping is just any link from one set of values to another. Some send each input to its own private output, one-to-one. Others let several inputs share a single output, many-to-one. Both are allowed because each input still lands on exactly one place. Only one pattern is banned, one input fanning out to many outputs. That breaks the golden rule and is not a function at all. So the test is simple. Read left to right and make sure no single input ever splits into two. Every function carries two sets with it. The domain is the collection of inputs it is allowed to accept, and the range is the set of outputs it can actually produce. Picture the curve. The domain lies along the horizontal axis, the range along the vertical. Sometimes we deliberately fence off the domain. Take y equals x squared, but only allow inputs from 0 upward. Now every output is 0 or positive, so the range is y greater than or equal to 0. Restricting what goes in tightly controls what can come out. Wire two machines together, and the output of the first becomes the input of the second. We write f of g of x, and the crucial point is reading order. The inner function g runs first, then f acts on whatever g produced. Right to left always. And order genuinely matters. Doing g then f usually gives a completely different answer from doing f then g. Suppose f doubles and g adds 3. Then f of g of 2 is 10, but g of f of 2 is only 7. Swap the machines, change the result. The inverse function runs the machine in reverse. If f takes 3 to 7, then f inverse takes 7 straight back to 3. It undoes whatever f did. To find it, we swap the roles of x and y and rearrange to make y the subject again. There is a beautiful picture for this. Plot a function and its inverse together, and each is the mirror image of the other in the line y equals x. Reflecting across that diagonal swaps every input with its output, which is exactly what taking the inverse does. One catch: a function only owns an inverse if it is one-to-one, because the reverse trip must land on a single value. That is why we so often restrict the domain first. It turns a many-to-one function back into a one-to-one one, just so the inverse can exist. Last comes the modulus, written with two vertical bars. It simply strips away any minus sign, returning the size of a number regardless of direction. The modulus of -4 and the modulus of 4 are both just 4. Distance from 0, nothing more. On a graph, the effect is striking. Wherever the line dips below the axis, the modulus flips that part straight up, reflecting it in the x-axis to give a sharp V. Everything that was negative becomes positive, so the whole curve now sits on or above 0. Here is the whole unit as one poster. A function is a machine with one rule. Each input gives exactly one output. The domain is the set of inputs you allow, the range is the set of outputs you get, and a mapping counts as a function only when it is one-to-one or many-to-one, never one-to-many. On the right sit the three operations you do to functions. Composite f of g of x means g acts first then f, and swapping the order usually changes the answer. The inverse runs the machine backwards, a mirror image in the line y equals x that exists only when the function is one-to-one. The modulus takes the size of a number, folding any part below the axis up, and the boundary fence so you do not over-revise. The named functions, the trig, exponential, and log ones, arrive in their own later units. The finer detail of graph transformation sits with curve sketching, and differentiating or integrating any of these is a calculus job for later. Here it is just functions. Define them, combine them, reverse them, and the modulus.